Yes, so I think in the interest of time, we'll just go ahead and get started. We're a little bit 10 minutes over time. So I guess everyone knows that the nature of this little Saturday workshop each fall is that each of the constituent participating states, Oregon and UBC and universities in Washington, nominates a representative, and it's my pleasure to introduce the representative from Oregon, Sun Yuan. Sun is just joining us this fall from the past 2 years as a postdoc at Carleton University in Ottawa, and he's now a postdoc at Oregon State University. And with that, I give you and who works in numerical methods for stochastic differential equations and optimization and control. So, Sun.
So thank you for giving me an opportunity to talk in the seminar. So I'm going to talk about the linear-quadratic-Gaussian mixed game with continuum-parametrized minor player. This one is a joint work with Dr. Huang in Carleton University. So I'm going to talk about the mean field dynamic game model. So this model will contains two kinds of players. The major players will have a strong influence to other players, and the minor players have a weaker influence to other players. So here's the contents of my talk. So this talk is related to the stochastic game with large number of weakly interacting players, and it is motivated from the complex system arising in engineering and psychoeconomics problems. For example, in industry dynamics with many firms or wireless network resource management, or surface hurting receiving individual predation risks by joining the group. So we can see in these pictures the fish join a group to produce bricks from predators. So these pictures are taken from the National Geographic. So for this kind of system, there are two key features. The first one is that each agent only receives a negligible influence from other individual, and the effect of the overall population is significant to each agent. And because the number of the players are very large, so we cannot expect that each player can collect the state information of all other players. So for the control problem, we want to develop a low complexity solution that each player just need to use its own state information. So that kind of strategy is called a decentralized strategy. So the class of games we consider here involve a major player and a large number of minor players. The major player has a significant role in affecting others, and minor players have weaker influence. And the minor players are parameterized by continuum parameter. So this research is motivated by socioeconomic problems. So it describes the interaction with one or more large corporations and many smaller competitors. So the objective of my talk is to design the decentralized strategies and establish an asymptotic Nash equilibrium property. So the method to be used is backwards SDE, backwards stochastic differential equation. So let's consider the dynamics of the players. So the dynamics of the major player is described by a linear stochastic differential equation like this. And the second equation is the dynamics of representative minor player. So xn stands for the average state of minor players. So it is average states of x sub 1 to x sub n. And u naught and ui here are controls. And the minor players are parameterized by smart parameter theta sub I. And we assume that the Brownian motions w naught and wi are independent standard Brownian motion. And the matrix A, B, and F, and D are continuous, are constant matrix and have compatible dimensions. So the cost for the major player have the quadratic form. And the cost of the minor player has this form with some mean field coupling term. So xn here stands for the mean field term. And the appearance of x sub 0 in the cost of the minor player shows the strong influence of the major player to the minor players. So for the game problems with larger number of players, the decentralized epsilon-Nash equilibrium was considered by Huang, Peter Keynes, and Mahame in series of papers. And for the decentralized control for large population stochastic multi-agent system was considered by Li and Zhang in 2008. And the midfield equilibrium condition for nonlinear system was considered by Lasserie and Lyons in 2006 and 2007. And the application for Markov-perfect industry dynamics with many firms was considered by Wen Chao. So more related to our talk, the case that the parameter set theta, when the set is finite, then the problem was considered by Huang in 2010. And in this paper, he used a Markov state space augmentation approach. So he aggregates all parameters, all equals parameters in the same set. So the system is reduced to finite dimension problems. So in our case, when the parameter set is infinite, then it is not applicable. So we directly treat the midfield process as a random process, and we use a backwards SD approach by Bismuth, and the model of a leader of major minor players was considered by Young in 2002. Is the model of leader and follower players. And we also use a maximum principle of SDE. So another kind of maximum principle for midfield problems was considered by Anderson and Ziherchi in 2010. So we assume that the initial state x sub 0 are independent and have uniformly bounded second moment. And the joint empirical distribution of the parameter and the expectation of the initial states converge quickly to some distribution. And we assume that the matrix A, B, F, and D are continuous functions for with respect to theta, and the parameter set theta is a compact set in D-dimensional space. So when the number of the player tends to infinity, then the midfield term tends to a stochastic process. And based on the linear property of the equations of the player, then we assume that the limit has this form. Here f1, f2, and gsd are deterministic function, and this function will be determined later. And after we approximate the midfield term by a stochastic process z, then we get a limiting problem. So we get a limiting problem for the measure player. So in here, the midfield term is replaced by a stochastic process. So we get a stochastic control problem with a random coefficient z. So using the method by Bismuth in 1976, we can solve this optimal control problem, and we can show that the optimal control for the limiting problem has this form. U bar naught has this form. This control depends on the state of the measure player. And another process, nu sub-zero. And nu sub-zero is a stochastic process, and it is a unique solution to a given forward-backwards SDE. And the matrix P naught T here is the solution of the Riccati equation. And now we apply that optimal control, and we want to show that the optimal dynamics have this form. So this form is similar to the form of the process Z with the 3 coefficient functions. So the first function f x naught 1 is a function of function f1. And we can show that the second coefficient f x naught bar 2 is a function of f2, and the last function g of x naught bar is a function of g. And we can compute this operator directly. And here, the kernel phi sub 0 is a unique solution of a given ODE system. So we can compute the dynamics of the measure, the optimal dynamics of the measure player that explicitly. So after we can solve the limiting for the problem for the measure player, we can apply the optimal dynamics and the process Z to obtain the limiting optimal control for the minor player. So in here, the midfield term is replaced by the stochastic process Z, and is a cost function. X sub 0 is replaced by optimal dynamics x naught bar, and the midfield term here is replaced by Z. So we get another optimal control problem with random coefficient Z and x naught bar. So by similar way, we can solve that problem and get the optimal control of UI bar in this form. And UI bar still depends on the state of the agent I, and it also depends on another stochastic process, but this stochastic process is known. And we can represent the optimal dynamics for the agent I in this form. So the difference here is that the dynamics of the agent I also depends on the Brownian motion Wi, and also depends on the initial state of the agent I. And the coefficient functions can be computed by similar way. So the first coefficient function is a function of f1. The second coefficient function is function of f2, and the kernel J here is a function of G. And the third function here and the last kernel can be computed directly. And here phi is the solution of an ODE system. And all of these coefficient functions are linear continuous functions. So after we solve the limiting control problems, we can obtain the optimal dynamics for the minor player, and we have a consistency condition. So Z of t should be the limit when n tends to infinity of 1 of n of the optimal dynamic states. And by the formula for the dynamics of the optimal control for minor player, we get the second equation. So based on this equation, we can find the process Z. So we denote the operator gamma 1 equals the average of gamma theta 1 with the distribution theta, and plus another term. And the function of gamma 2 have this form, and the function of gamma 3, lambda is the average of lambda theta. Then the triple function f1, f2g should be the solution of this system of equations. So we call the solution of this system the consistent solution to the Nash certainty equivalence equation system. And under mu assumption, we can show that this system has a unique solution f1, f2g. So when we can solve this system, we can obtain the approximation for the mean field process. Now we can apply the mean field approximation to the finite system with last number of minor player. So we assume that we define the optimal control for the finite system by this formula. This is similar to the control law of limiting problems. But the difference here is that we only have finite number of minor player. So each player can use the information from its own state and the major player's Brownian motion. And after these control laws are applied, and we get the dynamics for the major player and the minor players. And we get the mean field here. And we can estimate the difference between the approximation process ZT and the mean field from the finite minor player. So it is this difference tends to 0 when n tends to infinity. And we can show that the set of control U hat J has a epsilon asymptotic Nash equilibrium property. So it means that the cost function for the J player, if we change the control of the J player, then the infimum of the cost function for J player is between the optimal control for the limiting problems, and the error should be epsilon. And epsilon is very close to 0. It tends to 0 when the number of the player tends to infinity. So let's consider a scalar model. So we consider a scalar model for any player with certain coefficients here. Here we consider the dynamics for the major player by this equation and the equation for the minor players by this equation. And we don't put the midfield term in the dynamics of the players. And we assume that the parametric set of the major player is from -1 to 1. And AI here has a uniform distribution on -1 to 1. So we can compute, we assume that the cost function of the major player and the minor player by this formula. And we can compute directly the approximation of the midfield process. So we can compute F1 and F2 by numerical method. And here's a kernel J, and we can obtain the midfield approximation. So when we can solve this one, we can construct the decentralized strategy for each player. So for the case that the parameter set is an infinite set, then the Markov state augmentation cannot be applied, and we can decide in the strategy based on the function space, and we can solve the system of deterministic equations, so it is computationally efficient. So next, we consider a midfield model with the stronger influence of the major player. We consider the dynamics of the major player and the minor player with the stronger influence of the major player. So the appearance of the major player in the dynamics of the minor players shows the stronger influence of the major player. And in this case, we assume that A, B, F, and G and D are fixed matrix, and it doesn't depend on parameters. So in this case, problem is complicated, more complicated in the sense that if we change the control of the major player a little bit to U0 plus delta U, then the dynamics of the major player will change delta x naught, and because the appearance of the major player in the dynamics of the minor player, then the state of the minor players will change delta xi, and because all minor players will be changed, so it causes a change in the midfield term. So when n tends to infinity, we approximate the midfield term by z, but now it's more complicated. When u is changed by delta u, then x0 also change, and the midfield change, and it is described by this system. So to solve this problem, we need a more flexible definition for the control problem. So we say that x naught bar, u0 bar, an equilibrium solution for with respect to a process z star if we have this inequality. Here x0 bar satisfies the dynamics equation, and the cost function for u0 bar is smaller than any other variations of u0 bar. And the equations of the variations is given in this equation. And the cost function is the same as the cost function in the first part. So we can, by this way, we can also construct the limiting control problems with the same limiting process Z bar, and we want to find an equilibrium solution x naught bar, u naught bar with respect to Z bar. And when we can solve this problem, we can construct the limiting control problem for the minor player. And for the minor player, we have x naught bar is an optimal dynamics from the first problem, and Z bar is given here. So by the same way, we can have this representation of the x naught bar. X naught bar also have this form where the first function is a function of f1, and the second function is function of f2, and the last function is a function of j. And similarly, the dynamics of the minor player also have this representation. And the first coefficient function of the minor player also is a function of f1, and the second function is a function of f2, and the fourth kernel here is a function of g. And the third function and the last kernel can be given explicitly by this function. So again, we let's average the state of all minor players, and we get another equation to obtain the limiting process z. And we obtain a fixed point operator, and from that we can solve for the limiting mean field process, and then we can proceed similarly, and we can obtain the epsilon-Nash equilibrium property, and we can estimate the performance of the approximation. So this method reduces the computation into the deterministic function space, and for certain problems we can compute directly by numerical method. So thank you for your attention.